Okay, guys, we're going to start chapter 6 today. If you look at the title for chapter 6, it's on gravity and electricity. And you might be thinking, why gravity and electricity in the same chapter? Well, the reason is there's a lot of similarity between gravity and electricity. You'll be able to realize that once we're done with this chapter. But the force of gravity and the electric force are very similar in how they behave, and how you calculate them. Anyway, I've thrown up some pictures on this slide of some things that remind me of gravity, because we're going to start talking about gravity first, and then the later half of this chapter we'll talk about electricity and the electric force. So this top picture here, okay, I think is a cool picture because it shows you the universe, or the solar system, part of it anyway. But what do you notice about the universe? What are the shape of all the planets in our universe? They're spherical in shape, right? They're round. How come? Because of gravity makes them that way, right? Imagine taking this object has a gravitational field. Well, it attracts things in all directions, doesn't it? What kind of shape do you get if you're pulling in all directions? So you go this way, you pull this way, you pull this way, you pull this way. What shape do you get? You get a sphere. So every planet in our universe is a sphere. You'll never see some cube planet or some prism-looking planet. This doesn't obey the laws of physics. All the stars, again, they're all round. Everything is spherical, and that's because of gravity. Let's go to this one. Okay, who is this? Isaac Newton. And what is it trying to show here? What's happening? Yeah, as the story goes, he was sitting under the apple tree, the apple fell, and he started thinking about why things fall. Okay, but he made an observation, but it wasn't good enough to just make an observation, was it, with Isaac Newton? Let's measure. How fast does it fall? Do all objects fall at the same rate? How does mass calculate into that? Does gravity on Earth, behave the same as gravity on another planet? Or let's say in all of the universe, for that matter. Does gravity here act like gravity everywhere else in the universe? These were some of the questions that Isaac Newton had. He studied it. He figured it out. This equation is what he came up with to figure out the force of gravity. Between two different objects, we're going to learn how to use his universal law of gravity equation here and be able to figure out the force of gravity between any two objects, not just between us and the Earth. But is there a gravitational field around your body? There is. You'll be able to calculate that. We can calculate the force of gravity on the moon or another planet, for that matter. Okay, this picture is one that we're not really going to talk about all that much. It has to do with Einstein and how he thought of gravity, but he answered the question, why does gravity happen? You ever wondered that? Why? Yeah, we can calculate the force of gravity, and we know that if we drop something, it's going to fall down toward the center of the Earth, right? But why? What causes that? And that's what Einstein was thinking about. And this is a depiction of what his conclusions about why gravity occurs. And so we won't talk so much about that because it involves mathematics that are a little bit too complicated for first-year physics course. So anyway, we're going to study Isaac Newton and the equations that he came up with gravity. Okay? So if you're watching the video, please have your guided notes out. Again, it's chapter 6, guided notes. And here we go. Okay, so let's start with why do objects fall toward the Earth? Well, the ancient Greeks thought it was just the nature of things to either float or to sink. And we know if you drop your pen, it's going to sink, right? But what about a helium balloon? It floats. They said it was just their nature to do that. It didn't really delve into it any more any further than that. And so that's what we thought at that time until Galileo and Isaac Newton later on. They said it was a force of attraction between two bodies that have mass. So as long as something has mass, like this remote and this pen, is there a gravitational field between them? As long as they have mass, there's a gravitational field between them, and they looked at it like that. So they actually quantitatively figured out what the force would be and calculated it. Well, Einstein come around, asked the question, well, why is there gravity? You ever guys think about, yeah, it's a force and it falls at 9.8 meters per second squared, but why does it happen? And that's the question Einstein was asking. He came up with this. It happens because there's a curvature of space-time about objects with mass. And so if you go back to this. Let me go back to this picture here. A curvature about space-time with objects with mass. And so if you imagine like a bed sheet, had four people holding the corners of the bed sheet, that would be your space-time. That's this graph right here, space and time, where space and time meet. Well, if you put a heavy bowling ball on that bed sheet, what's going to happen to the bed sheet? It's going to have a curvature to it, right? Einstein said that's what causes things to be attracted to other objects with mass, is that you're curving space-time. So, of course, if you put a smaller object next to a large bowling ball on that sheet, it's going to do what? It's going to fall into it. It might start coming around like this, but then it will eventually hit that heavier object, right? And so we won't study much of what Einstein came up with, but that's a little introduction about how gravity works. It's a curvature of space-time. Okay, let's write down a definition for gravity. In your guided notes, here it is. Gravity is a long-range force, and it acts over a distance. So it's a long-range force. Do you have to be touching another object in order for gravity to work? No, it acts over a distance. That's what a long-range force does. It's not a contact force. And that's one of the cool things about gravity, is that you don't have to be touching and it still works. It acts over a long range. Gravity accelerates all objects at the same rate. We've proved that in labs with calculations, and we've also seen that two objects will fall at the same rate. That rate is called g. And near the Earth's surface, g is equal to what? G is equal to a negative 9.8 meters per second squared. Again, negative because it always pulls things down. The force of gravity near the Earth's surface is equal to mass of the object times g. So if we want to figure out the force of gravity, it's equal to the mass of the object in kilograms times g. We've learned this equation the whole year, haven't we, guys? Force of gravity is equal to mg. What's another way of saying force of gravity? Weight. Your weight is the same thing as the force of gravity. So if you know how much you weigh, you know how much force gravity is pulling you down toward the center of the Earth. Gravity acts on objects with mass. You have to have mass in order for gravity to act upon you. But here's the thing. The more mass an object has, the larger the gravitational force will be. And we've seen that before. If you have more mass here, if this number gets larger, what happens to the force? Well, it's also going to get larger. Okay. So Isaac Newton and the apple, I got a little animation of it over here. So as the story goes, it hit him in the head, but we don't really know if that's true. Maybe he just watched it and he observed that it was falling down and asked questions. But one of the things that Isaac Newton started to wonder about was gravity that's pulling this apple down from the tree toward the earth. Was that gravity the same on Earth as it is everywhere else in the universe? What do you guys think? And he figured out that it was. It behaves the same everywhere in the universe. And so, what does it say here? Is that same thing responsible for keeping the moon in orbit? Not entirely accurate, but it's a good story. What that means, not entirely accurate, was the apple hitting him in the head. But it is accurate when he figured out that gravity on Earth is the same gravity behaves the same everywhere in the universe you go. So what we learn here are going to be is an equation that Isaac Newton came up with that works everywhere in the universe. In fact, NASA lands the Mars rover on Mars. They can figure out how much the force of gravity is going to be on Mars with this equation. And it's incredible to know that Isaac Newton came up with that hundreds of years ago. Okay, there's two factors that affect gravity. One is obviously the object's mass. The heavier you are, or the more massive, what happens to the force? It goes up. Okay? So as mass goes up, so let's write that down. Force of gravity is equal to mg. As mass goes up, what happens to force of gravity, guys? It goes up. What kind of relationship is that? It's a direct relationship, right? As one goes up, so does the other one. What if mass was to go down? Force of gravity goes down. Again, see how it's a direct relationship? If one goes up, the other one goes up. If one goes down, the other one goes down. Okay? Well, obviously mass is one of the factors that affect the force of gravity. What's the other one? The other factor that we haven't learned about yet is distance. The distance between the two objects also affects the force of gravity between them. So the distance between the two objects. Let's kind of let's try to think about how distance would affect the force of gravity. Okay? So here's my two objects. How does the force of gravity act here as compared to, let's draw them like this now? Which one's going to have a stronger force of gravity? The top or bottom illustration that I just did? This one's going to have a stronger force of gravity, right? This one's going to be weaker, and you're exactly right. So distance does affect the force of gravity as well. So let's look at this. The force of gravity is directly proportional to the mass of the two objects. Directly proportional, that just means as one goes up, the other one does what? Goes up. So as mass goes up, force of gravity goes up. The larger the masses, the larger the force. The smaller the masses, the smaller the force. Okay? So I've got a picture here of our solar system. In 6th grade, you learned all of the planets, right? What planet is this one? Mercury. Did your teacher teach you a mnemonic?
Yeah.
My very energetic mother just served us nachos. Did you guys learn that one? 9 pizzas. Yeah, same thing. So, what planet is this? Mercury. Very is for what? Venus. Energetic? Earth. Mother? Mars. Just? Jupiter. Served? Saturn. Us? Uranus. And nachos? Neptune. And then there's Pluto, but it was kind of demoted a few years back. It's a little bit too small for them to consider it a planet. So, all right, where was I going with this? Oh, mass, how it affects gravity. So, Jupiter is the most massive planet. How is your gravity? What would the force of gravity be like on Jupiter? Higher or lower? It has more mass, so what should the force of gravity be? It should have a lot larger force of gravity, right? And we'll do a lab where you're going to figure out how far you could jump on Jupiter. If it has so much stronger gravity, you'll figure out how far you could jump. And so it'll be a little interesting to see that. Which one do you think you would have the lowest force of gravity on, or the lowest weight? Pluto, yeah, Pluto, definitely. What about, this is a popular one, the moon. How does your force of gravity affect you on the moon? It's 1/6 that of Earth. Good. And so, yeah, force of gravity is 1/6 on the moon. Anyway, so we'll do a lab on that. Okay, let's look at the relationship between gravitational force and distance now. How does distance affect the force of gravity? Well, the force of gravity is inversely proportional. What does inversely proportional mean? Yeah, as one goes up, what happens to the other one? Goes down. Okay? But it's inversely proportional to the square of the distance between the two objects. This gets a little complicated for students, so let me start slowly. If I give you a number, say 5, what's the inverse of 5? The inverse of that would be 1 over 5, right? So you take the inverse of something, you're just putting 1 over the top of it. Okay? So let me read this definition again. Let's focus on this. The force of gravity is inversely proportional, so we put 1 over it, to the square of the distance between the two objects. So that sentence put into an equation is right here. Force of gravity is equal to 1 over the distance between the two objects squared. Okay. Force of gravity is equal to 1 over the distance between the two objects squared. So, let's see if we can get this, see if we can reason around this equation here. It says the larger the distance between the objects, the smaller the force. What if the distance between the two objects, so here's one object A and object B. What if B moves back and say it comes over to here? How is the force of gravity going to be affected by that? It's going to go up or down? It's going to go down. So yeah, like the larger the distance between the objects, the smaller the force. Okay? And so we can actually calculate that, and that's what the rest of the lesson will be today on, is how to calculate how much less will it be. Okay, we want to quantify that. Okay, let's go to this one. The smaller the distance between the objects, the larger the force. So now what if B moved closer and this was B? Now the force of gravity goes up. So as distance gets smaller, force of gravity goes up. As distance gets larger, force of gravity gets smaller. Okay, that's an inverse relationship. All right. In fact, the force of gravity follows this scientific law that's present in a lot of different places in science. It's called the inverse square law. You're supposed to write down the definition in your guided notes, so I'll give you a second to do that. The inverse square law describes how force, sound, and light change as a result of the distance between the objects. Describes how force, sound, and light change as a result of the distance between objects. This is the inverse square law. Okay? Something is equal to 1 over the distance between them squared. So force is equal to 1 over d squared. That's the inverse square law. Why is it called the inverse square law? Well, inverse is 1 over it, over something, and squared is we're squaring the distance between them. Okay, so it's called the inverse square law. We're going to use this law a lot in this chapter. So let me give you an introduction to the inverse square law. Inverse square law can be used in a lot of different applications in science. Okay, it can be used for the pull of gravity. Gravity either increases or decreases based on the inverse square law. The push or the pull of charged particles, so how an electron pushes on another electron, follows the inverse square law. Or the force between a proton and an electron follows the inverse square law. We'll cover that in the second half of this chapter. Light intensity, so this light that's coming from the light bulb in this room changes by the inverse square law. You get closer to the light, does the light get more intense? Yeah, and as you get farther away, it gets less intense. We'll go over that. Sound intensity. How people hear your voice changes by the inverse square law, and we'll have an example on that. Magnetic forces and also radiation, nuclear radiation, changes by the inverse square law. All right, here's an illustration I've got that shows how light is changed by the inverse square law. So, inverse square law, so this is light, so let's talk about intensity. Intensity of light is equal to 1 over d squared. If I asked you what the intensity of light is at 1 meter, it doesn't say here, but let's just say this is a meter. What would the intensity be? Well, if we're 1 meter away, let's put in 1 meter for the distance. So what's 1 over 1 squared, guys? That's 1. So its intensity is 1 whatever. They measure intensity. Now, how would that change if you moved twice as far away? Now you're moving twice the distance away. So let's figure it out. 1 over, what's the distance now? 2. Because you moved twice as far away. What's 1 over 2 squared? 1/4. So as you can see, guys, I want you to listen to this. This is important. A lot of students will say, if I ask this question, how is the intensity of light changed if you move twice as far away? A lot of students will say it will decrease by half. Is that right? No, it doesn't just decrease by half because we're squaring it here. It decreases by how much? 1/4 the original intensity. So always remember that you've got to square this bottom number, so it's not just going to decrease by half, it's going to decrease by 1/4. Okay. You can continue working that out all the way through. Let's just do one down here. Let's do 7. So what's 1 over 7 squared? 149. What does that mean? It means that the intensity at this point is 149 what it would have been at 1 meter. So it's decreasing a lot, right? I've got some example problems with the inverse square law. So let's go through them. I think I've got 3 practice problems and then I'll be done. Okay? Here we go. How much greater is the light intensity from a flashlight at 1 meter as compared to 4 meters away? As with all physics problems, I like to draw a picture. Okay, let's draw a picture of your flashlight here. I don't know how to draw a flashlight. Okay, there's my flashlight. Let's say you were standing 1 meter away. So from here to there is 1 meter. Oops. Let's say it's asking how does that compare to light at 4 meters away. So let's say you backed up 4 times that amount. So you're clear back here now. How is light intensity going to compare? And we can solve this problem using the inverse square law. So let's write this down. Intensity of light is equal to 1 over d squared. Now these problems become way easier if you will think about them in proportions. And what I mean by that is what I'm going to explain right now. How much farther away did you move if this right now is 4 meters? Don't think of it in terms of the actual meters away. How much farther away did you move? How many times farther away are you now? 4. You are 4 times farther away. So in for D, we are going to substitute in 4 because you're 4 times farther away. So 1 over 4 squared is equal to what? 1/16. So because you made a proportion out of it, this is 1/16 what? What is the what so 1/16 what?
Of the original light.
Of the original light intensity, right? So intensity is equal to that. So back here, this guy is going to be how much greater is the light intensity from but we kind of answered that wrong, didn't we? If you read it, this guy is going to feel 1/16 the intensity of light that this guy feels. So how much, let's reread it. It says, how much greater is the light intensity from a flashlight at 1 meter as compared to 4 meters? So how much greater is this intensity compared to this guy? 16 times, right? Greater. Does that make sense, guys? Make sense? Okay. It gets a little confusing. You got to make sure you answer the question that it's asking there. This one would, if it asked it that way, would be 1/16 the light intensity. But it asked it, how much greater is this one feeling it? Well, it's 16 times greater. Okay, practice problem number 2. Now this is a challenging one. Let me go through it with you. A person that is 20 meters away shouts and you hear it at 40 decibels. If you were standing 10 meters away, how many decibels would you hear? Let's draw the picture, okay? So here's your friend, and they're shouting something. So that's my attempt at a shout. Okay, you're standing, what does it say? 20 meters away. So here you are.
10.
Okay, let's read it. A person that is 20 meters away. Okay, so let's say you're right here. Okay, from the person that shouts to you is 20 meters away. And you hear it at 40 decibels. So you're picking it up at 40 decibels is just a unit for measuring sound volume. Okay. Now it says if you were standing at 10 meters away, so you would have to get closer, right? By what proportion, what factor? Always think in terms of factors. How much closer are you now? Your distance is now 1/2 what it was before, right? Because you're at 10 meters here. If you measured it there. Okay. How many decibels would you hear it at? So always set this problem up as a proportion and figure out the factor by which it changes. So decibels, or sound, follows the inverse square law, 1 over d squared. And we can use the inverse square law to figure out what proportion it's going to change by. So we want to know how many decibels this guy hears it at. Now before we even solve it, is he going to hear it at more decibels or less decibels? It's going to be more. More than what? More than 40. So if you get an answer that is less than 40, you know you're doing it wrong. You're thinking about it wrong. Okay, so it's got to go up. We know that. So let's figure this up in terms of proportions. Okay, so here's how I would do it. How does the distance that this guy is at compare to this guy? It's 1/2. And so I would set it up like this. It's equal to 1 over 1/2 squared. Because the distance that he's related to the other one is 1/2, isn't it, guys? So proportionally, he's 1/2 the distance as the other guy. Does that make sense? Okay, now let's solve the mathematics of it. What does that equal? Well, 1 over 1/2 squared is, what's 1 squared? 1. What's 2 squared? 4. What's 1 over 1/4? You guys ever heard that multiplication is just,
4.
or division is just multiplying by the reciprocal? Division is just multiplying by the reciprocal. What's the reciprocal of 1/4? 4. So let's take 1 and times it by 4. It equals 4. Okay? Does that make sense? Or you can put it in your calculator, 1 divided by parentheses 1/4. Okay. Well, when you get that out, does that mean it's 4 decibels? No, we set it up as a proportion. Remember, this was 1/2 what the other one was, so we set it up as a proportion. This means 4 times something. 4 times the original decibels. Okay, so this is 4 times what it was before. So if it was 40 right here, what's 40 times 4? 160 decibels is your answer. Okay, so this guy's going to hear it at 160. Yeah, it's extremely loud, right? Yeah. So. Okay, very good. I think students get into problems where you get to the end here and you've solved it. You know that it's 4, but you don't realize what it's 4 of. It's 4 times that amount of the original value because we set it up as a proportion here. Anyway, I'm going to go through a lot of examples with you. Okay, I've got one more for this video. Practice problem number 3. It says the force of gravity between 2 spaceships is 100 newtons. What would the force of gravity between them be if they tripled the distance between them? Okay, I always like to draw a picture. I don't know what a spaceship looks like, but I'm going to draw it like that. Okay? Let's draw the other spaceship kind of closer. So between them, they feel how many newtons of gravity? 100 newtons. Okay, that's the force of gravity between them right now. But it says, what would the force of gravity between them be if they tripled the distance? So it didn't tell us what the distance was here. We don't know it. Okay, but this guy is going to move back, clear back here, so that now it is, if we don't know distance, how can we describe it in terms of the distance originally? We don't have an actual distance value, so what do we say? Yeah, this is going to be 3D. 3 times the original distance. Okay. All right, now we know that force of gravity follows the inverse square law. So let's write the inverse square law down. What are you going to substitute in for D here? What are you going to substitute in for D?
1/3.
Would it be 1/3 or would it be 3 or what would you do?
3 because you're triple.
Yeah, you're tripling the distance between them. When they get farther away, this number is going to get larger, right? So it's equal to 1 over 3 squared, which is equal to what? 1 over 9. So 1 over 9, is that my answer? No, what does that tell me? It tells me the proportion by which the original value changes, right? It tells you by what magnitude you should times your original value by. So if these guys felt 100, obviously if it moves back it's going to be less, but by how much less? 1/9. So here's how you figure it out. You take the original value and you can times it by 1/9. Or just divide by 9, whatever you prefer to say. What is 100 divided by 9? 11.1 repeating. 11.1 what? What's my units? Yeah, we were measuring that force in newtons, so these guys would have a gravitational force between them of 11.1 newtons. Does that make sense, guys?
Yeah.
They're closer, it's 100. they move 3 times farther away, we can actually calculate the force of gravity between them at that point. Again, when you get to the end, guys, it doesn't mean your newtons is 1/9 newtons. It means this is a proportion by which your original value changes. Correct? Okay. All right. To give you some more practice on this, and I'm going to go through it with you for a while, there is a worksheet in the student workbook titled Inverse Square Law Worksheet. Please go there. It's called Inverse Square Law Worksheet, and hopefully this helped.